Well, please welcome Dr. Harris.
Good evening. It's a real pleasure to be here. Thank you for coming. Most of the talk today will be on examples of visual mathematics from pure math. But since I am at Microsoft, let me tell you one applied problem, which is finding sparse cuts in a graph, where the technique came from a pure math problem on understanding mixing of Markov chains. So what is the applied problem? Here. Okay. So this was joint work with Reed Anderson, who was at Microsoft, and as well. And the kind of problem we have concerns various big graphs, and these numbers are all not fully up to date on. So the web hyperlink graph, query click graphs, advertising keyword graphs, and the smallest one of these is the US road networks. And in all these graphs, what we want to do is to find the community of a node. Now, the graph which will be easiest to visualize is not any of these practical graphs, but the following random geometric graph, where we just throw down nodes at random in a square and connect any two whose distance is below some threshold r. So this is a random, or delta. This is this random geometric graph. And again, the goal will be to find the community of a single node, and that's something that gets used in many applications when you want to, as we do at Microsoft and people do at Google, to store an image of the web on a small number of computers. You still have to decide how to partition it between those computers, and you want to partition it in such a way that most of the links are happening within the RAM of one computer rather than from one to the other. So this is an example of a graph partitioning problem. And another one closer to what I'll discuss is local graph partitioning. We have a single node of interest, maybe a single website, and we want to find a community of that node, which has a lot of interconnections and relatively few connections to the outside. So think of a network of 100 billion nodes. We have a single one, and we want to find a community of maybe 5,000 nodes around that. And we want the work we do to be related more to the 5,000 than to the 100 billion. So that's the kind of challenge of local partitioning. And here are, so it's a targeted version of the sparsest cut problem. So here are some of, in the road network, we can kind of geometrically find good cuts. But, the bigger network is is the advertiser and keyword network, where we connect an advertiser to a keyword if that advertiser made a bid on advertising with that keyword. And there are many applications to this kind of local partitioning problem. And it's also used as a subroutine for other partitioning algorithms. So I won't go much more into the theory, but instead just show you how the evolving set algorithm works for this problem. So let me go to that slide. Okay. So here we go. So again, we're going to illustrate this with this random geometric graph. So given a starting node, let me start the process again. So this evolving, so what the first naive way, if we want to build a community of a node, or think of community of the friends of a node on Facebook or a person on Facebook. So the first naive thing you do, well, let's look at the first order friends, then second order friends, then third order friends, and this will this is what's called breadth first search, and it will very quickly cover the whole network. But it is too crude. It doesn't distinguish beyond the first order frames. When we go to second order, there are many different kinds of second order frames, right? Some are richly connected to the central individual via many connections, and others much less so. So when we want to find a real community, we don't want just to do this crude breadth first search. And what this algorithm does is, you can think of it as a smarter version of breadth first search. And again, this algorithm was developed for another purpose in joint work with Ben Morris back in 2003, and it's closely related to older work of Diaconis and Phil from 1990. And so how does this process grow? Given a starting node, for each of its neighbors, we think, are we going to add it to the cluster or not? The probability we'll add it is just the fraction of the neighbors of the node in the current cluster. So as this cluster grows, every node enters with probability, which is its fraction in the current cluster. But as you see in this picture, this process we have here is not monotone. So for every node, we also have a chance to remove it from the cluster, and that probability also is according to the fraction of its nodes outside the cluster. So this cluster grows and shrinks, and as it grows, it is really designed to capture good communities of the set. So if you let it run forever, this process, I mean, one thing I didn't add, it's conditioned not to disappear, so it will never actually shrink to a point. And after this conditioning, it has to absorb in the whole space. This will take a very long time. We don't want to wait that long. But as in the process where it's growing and shrinking and eventually growing, it goes through sets that are very good communities of the initial node, namely they have relatively few edges to the outside compared to edges to the inside. And being able to visualize this on a random geometric graph is helpful in developing the algorithm. So to this example, let me turn to examples more from pure math. And so one of my goals would be to explain what you're seeing in this picture, which is the abelian sandpile. But let me start with a different one, which is the... Okay, so remove this. And let me start with a model called the rotor-rooter. So this is a model first developed by Prijev and colleagues under the name Prijev Dar and colleagues under the name Eulerian Walkers, and then by Jim Prop under the name rotor-rooter. So let's look what this model does. So this will be a growth model where we will add nodes at the center or add particles at the center, I should say. And each time we do that, the particles will eventually spread out according to the arrows. So specifically, the rule is when we add the particle, we add it always at the center. First, rotate the arrow by 90 degrees, and then move according to the direction of the arrow. And if this location is unoccupied, the particle settles there. Again, we add a new particle at the origin. Okay, so we add the particle, rotate the arrow, move to an unoccupied spot, and stay there. Now the next particle, again, moves up here and settles there. Now the following particle will move to the right. That location is also occupied, so the arrow will rotate and will settle where in the next step, and so on. So now each time I'll press the button, we'll start one particle at the center and we'll just see its whole trip until it settles in an occupied spot. So this is called rotor-rooter aggregation. And one question that Jim Prop asked back in 2003 is, well, what shape is this leading to? Can anyone guess? Circle. Okay, let's run it faster. And indeed, it's a circle. So this, Jim already knew the simulation, but he couldn't prove this is going to a circle, and this was something we did together with Lionel Levine in around 2006. Now, although we can prove that the limit shape is a circle, it is much more circular and much more perfect than the proofs are showing. So let me try and get a picture of how this looks. So this is the rotor-rooter model with the million particles. Okay. So
the colors of the directions of the arrow, right?
Exactly. So each node is colored by the direction of the arrow, and you see there's a pattern of the colors. But first, I want to dwell on the circularity. So in 2003, Jim asked us to show that the ratio of the in radius and the out radius of this shape goes to 1, so it does scale to a circle. We first showed some bounds on the error, but the bounds were of the form some power of the radius. Just in 2016, we improved the result to show that the fluctuations are at most logarithmic. So if we look at the radius, how it changes as we go around, it's at most log of the number of particles. But in fact, what the simulations indicate is that it's much, much rounder than current math can show. So if we look at the difference of the in radius and the out radius, so from the center to the closest point on the outside and to the furthest point, this difference never exceeds 2 in all our experiments. So it's basically as round as it could be, given that it's a lattice set on the lattice. And this is, again, beyond current technology to prove such a precise picture. Now, I'll say a little more about the pattern inside, but one thing which there is remarkable persistence of this pattern. So what do you see in the shape here? This is what results when you start, instead of at a single center, you start at 2 different centers and put particles in both locations, and they're moving according to these rotor rules. Maybe we'll go back to the simulation to see that. And so let's start with 2 centers. So when we start with 2 centers, initially they form disks, but when these disks merge, we get this shape. Now here, if I fix the locations and let time grow, eventually this will become a disk. So the right thing to do is to time it just right to get the more interesting picture, and basically stop it at a time which is the square of the distance between the initial points. And then we get this interesting picture, which it actually follows from results of Aharonov and others in complex analysis, that if we look at this shape, the boundary is a algebraic curve of degree 4. So you can write a formula for the boundary here, which is a polynomial in 2 variables of the 4th degree. And in general, if you start with k points, like with 1 point you get a circle, which is a quadratic polynomial. If you start with k points, it's known that you get a boundary which is described by a polynomial of degree 2k. So of course, you know it if the points are far, because if you want to write an equation for k circles, you can write it as one equation of degree 2k. But the interesting thing is it's still true even if you start the points close and you get this kind of shape. So that's the rotor-rooter, and now some of you have seen the shape that was up before the lecture started, so let me get that simulation going again. So this is a simulation due to Alexander Holroyd of sandpile, and let me start. This is the relevant simulation. So maybe before going on with the simulation, I should show you something of what this process is. So this is the abelian sandpile, a model invented several times independently in statistical physics by Bakhtin and Weisenfeld, and then developed much further by Deepak Dar, who's made the most contributions to this model. And it was independently invented in combinatorics slightly later under the name of chip firing by Lionel Levine and Shor. It has connections to many areas of mathematics, and I won't go into these here. So what is the model? Let's think of it in 2 dimensions. So think of d equals 2 here. So every location in the lattice has 4 neighbors. And we start with some configuration of chips, or later we're going to add more chips or particles at the center, as you saw in the picture. And the rule is whenever a location has 4 or more chips, they topple, and one goes to every neighbor. So let's see this in an example. So say we start with 16 particles at the center. So I said when you have 4 or more, you send 1 to each neighbor. So this is the fair division that I was referring to. So fair division is is used more in economics, but here I'm focusing on math examples where the point is to divide very fairly between the neighbors. So each one of these, so we have 1 particle toppling to each neighbor. We still have 12 in the center, so we repeat. 1 particle goes to each neighbor, and we get 2 in each neighbor. Repeat again, topple, and repeat again. Now there's 0 at the center, but there are 4 at each of these sites. So now they can topple as well, because they have enough to topple, so each of them topples. So, for instance, when this one topples, we get this picture. And we keep going and toppling these 4s, and we create a new 4 in the center, which also needs to topple. And this configuration is called stable because there's no location with more than 3 particles. So this is what you see in this simulation, just run faster. So again, this is this one. So here, instead of starting with a fixed number at the center, I keep dropping sand in the center, and then the toppling is the same as you saw before. And we start getting this shape. And naively, when we were looking at this shape, we thought, well, this should also go to a circle. But it turns out that it really doesn't. And this was realized before us, certainly by Deepak Dar and others. Here is let's see. Okay, here's what it looks like with 1,000,000 particles. So you have, so it's roughly a 12-sided polygon, but not exactly. So you see there are some 12 flat sides, but between them there are some rounded shapes. And now what do the colors mean in this picture? The color represents how many chips are in each location. So it's either 0, 1, 2, or 3. The blues are 3s and so on. So you see a pattern, and the amazing thing is if you do this with 100,000 particles, with 1,000,000 particles, or with 1,000,000,000 particles, the pattern looks the same. Even though the growth here is not growth by expansion, it's growth by this kind of toppling procedure. Initially we couldn't prove that there is a scaling limit for this picture. So for the rotor, we know there's a disk scaling limit, and we understand what happens with different starting configuration. Here, this was a harder problem, which was finally solved in paper of 2013 by Pegden and Smart, who showed that there is a scaling limit for the sandpile, although that is a much harder fact, and identifying it is still not completely solved. There's huge progress on that in work of Levine, Pegden, and Smart, but it's not solved to completely identify it. To understand this better, it's useful to look at other background conditions. So suppose that, let's start, go back to the simulation, and suppose that I change the background height. So in this picture, I kept adding sand at the center, and everywhere else was at height 0. So we could change this background condition. So for instance, here I'm going to start with background condition of all 2. So this means every location has initially 2 particles. So red stands for 2 here. And we keep adding particles at the center. Whenever a yellow indicates that we get a 4, so a 4 will topple. And you see here the growing shape just looks like a square. And this, in this case, is possible to prove. First proved by Fay and Reddig that you do get a square. But inside this square is a growing butterfly. And so the work of Pegden and Smart and Levine starts to explain why we will get this butterfly at all different sizes, but exactly why we get this particular butterfly is still not understood. One thing you can ask, so what happens with different boundary conditions? So I showed you 0 and 2. Another natural background condition is 1. So again, every location has 1 particle to begin with. You still need 4 in order to topple. And in this case, it seems like you get approximately an octagon, but that's still not proved. Now, empirically, when you add more and more, when you increase the background height, you get something with fewer sides. So I told you about background height of 2. What about background height of 3? Well, if you have background height of 3, then it turns out that if you have 3 everywhere and 4 at the center, then that's enough for the process to just topple forever without adding any more sand. So that's why we don't have background height of 3. But there are all kinds of interesting initial background heights. So for instance, this is background height of 3 in these blocks, but with these red rows between them. And these are enough so that if you start with a fixed constant number at the center, this picture will eventually stabilize in a very interesting pattern. On the other hand, in this skew lattice, so if we start here, then with a large enough initial configuration, you don't have to keep adding. If we just add a constant number of particles, this will already create infinite motion. And somehow there's enough wood here to create an infinite fire, even if we just add a small match at the center. So in all of these cases, both for the rotor and the sandpile, the visualization has been driving force in the analysis, and I'll show you some more examples of that. Any questions? So, show you one more example, which is actually the first of these kind of examples to be analyzed. What you see here is IDLA, internal diffusion limited aggregation, invented by Witten and Sander, and first analyzed by Lawler, Branson, and Griffith. So what's going on here? The colors still indicate the direction of the arrows, but the difference from the rotor story I told you in the beginning is that here the particles leave a site instead of in a periodic fashion, in random fashion. So you start at the center, and every particle moves to a random location, a random neighbor, until it finds its unoccupied spot. And for this one, so that original paper showed that the shape is asymptotically singular. That was back in 1991. The fluctuations were only understood 6-7 years ago in independent work of both Acela and Godelier and of Jerrison, Levine, and Sheffield, that the fluctuations here are logarithmic in 2 dimensions and even smaller in higher dimensions, But you see here that you can kind of see in this picture that the fluctuations are real. There really are these fluctuations of the boundary. It's not completely round in the random case. So the random case is completely analyzed. It's known due to the work of those authors that the fluctuations in 2 dimensions are indeed logarithmic. But for the rotor, we have the same upper bound, so the fluctuations are logarithmic, but there's no lower bound, and we suspect that there's more regularity to be found there. So one thing about the color. So you see in IDLA, this is again the direction of the rotors, but it's completely random, so you see nothing. While in the rotor picture, we saw this nice pattern of the colors. So this pattern is not completely understood, but there is some understanding due to work of Ostojic, and let me get to that. So, okay, so what do you see here? So this is the pattern that you saw before from the rotor, but we apply to it a transformation. And maybe I'll go back to so the transformation is z goes to 1 over z squared. So that's kind of reflection in the circle and squaring. And this will map the strange pattern we saw before inside the disk of the rotor into something which looks like a lattice pattern. You can see that. And although the sandpile is defined in a very, it doesn't lead to a circle, it looks somewhat different, but we have the same property as discovered by Ostojic, that when you apply this complex transformation, z goes to 1 over z squared, you get a lattice pattern. Although the colors here mean something completely different. Remember, in the rotor, the colors meant the direction of the arrow. In the sandpile, the colors mean the number of chips at every site. Yet the same map is playing a crucial role in both these examples. Here is one more mystery discovered by Dar. So it's discovered but not yet understood, relating a 2- and a 3-dimensional sandpile. So this is a critical 3-dimensional sandpile. So the dimension is 3, the background height is 4. So every site initially has 4 particles, and we keep adding particles at the center, and we get, a growing cube. So now in this cube, if you take 5 million particles, take this cube and examine it slice through the center. So we slice through the center, we get a square, and we get this pattern inside the square. So this pattern of colors, and again, the colors mean the number of chips. Now on the right, you have 2 dimensions, background height 2, and this carefully chosen number of initial particles at the center. And you get this picture, which is different from the left one, only in some circle around the origin. So if I look outside this circle, then these 2 pictures turn out to be identical pixel by pixel. So it's not just that they look the same, they're exactly identical outside some neighborhood of the origin. So this kind of dimension reduction of this model is still a bit mysterious. I said there's a lot of progress on, so this model, the abelian sandpile, is more difficult than the rotor. A lot of progress on it in recent years due to Pegden, Smart, Levine, and others. So the last 2 examples I want to turn to involve fair division in a different sense. And let me close this and get to those. So again, a case where visualization was a driver of the mathematical analysis. So this is a picture drawn by Ander Holroyd, and the relevant work is by Holroyd, Chris Hoffman, and myself. And so what do you see here? So there's a bunch of centers, and the goal is, we have a we have a square, it's actually a torus, so a square with periodic boundary. The left side and the right side are identified, up and bottom, top and bottom are identified. So we have this, this square, and we drop some 300 points at random in the square. So these are these centers you see here. The goal is to divide the square into territories where every center gets the same area. But the centers are given to you. They're picked at random and now they're given. How do you divide without kind of central control in a kind of distributed manner the square into equal size territories? So this is one method, and it's called the stable allocation. And one way to think about it is for every center you grow a disk at unit speed, and the center captures all the area it reaches first until it gets its quota, then it stops growing. So some centers are lucky, like this one, it will get all its area locally. But some centers are hemmed in and they have to find their area far. So if you look, so anything which is big here like this, if you look at this, it's part of the territory of this center. So this center grows a disk, but it's so surrounded that it only captures very little area near the center. But the disk keeps growing in the background until it comes up for air, much further when these are sated, and it completes the territory. So these territories are actually disconnected, but every center does get its fair share of area. So So some of the later work on this was also joined with Robin Diemantel and Odette Schramm. And again, so the kind of problem this addresses, and this will connect also to tomorrow's colloquium, I'll explain at the end. So again, the kind of problem is we have a random center. So if it's in this square, these are just uniform random points. If you're in the whole plane, it's natural to think of a Poisson process, just the limit of uniform points. And now the procedure I told you about, it grows a stable allocation. So it's not just a fair allocation, it's a stable allocation. What does that mean? So here is a center C and a point X. This partition would be unstable in the sense that C and X is not in the territory of C, but it's closer to C than to its center. And conversely, C has some points that are further than X. So C and X would prefer to match up than to have their current allocation. And this notion of stability comes from the work of Gale and Shapley. So Gale and Shapley in the 1962 wrote an influential paper. It eventually led to a Nobel Prize for Shapley and Roth, since Gale passed away before the prize was awarded. So they were considering more applied problems of matching students to colleges, or they gave the illustration of matching men to women as a stable marriage, where an unstable matching is a situation where a pair prefer each other to their assigned matches. And they showed that you always have a stable matching without any unstable pair. And they provided an algorithm to find that matching, and that algorithm or variants of it are used today in many applications, including assigning schools children to schools in the public schools of New York City, and residents to hospitals in many locations, and so on. So that algorithm can be used to realize the process I described to you before. So I told you a process where the balls are growing continuously, but to prove things about that process, this continuous growth is not convenient because there's too much dependence. So it's better to have a discrete procedure, and it turns out you can implement. This is again the Gay-Shapley story between, let's say, men and women or colleges and students, and we can imitate their algorithm in this geometric setting, and I won't go through it in detail, but this is the stage 1 applications. Every center applies. So I guess here it's every student applies to the closest center. So what are the students? The students are the points in the plane, and these are the centers. And what you get is known as the Voronoi tessellation. If we have centers and we just partition according to which point each point goes to its closest center, you get this process, this partition. So this is a very nice partition, but the areas are not equal. And by iterating the steps of the Gay-Shapley algorithm, you can convert to the same picture that I showed you in the beginning, in the limit. So, okay, let me stop with this example. And one thing that was less ideal in this partition is that the territories are disconnected. And Maxime Krikun came up with a nice way to get connected territories. This is his picture of that way, and it's based on drawing a spanning tree in the plane and applying conformal mapping. I won't get into the exact story, but it was very hard to analyze this, although the shapes are connected. To understand their sizes is still not known. And the kind of later twist on this is the method of gravitational allocation, which I will be talking about tomorrow in the colloquium, but I'll just give you a little example today. So, for motivation. So that's joint work with Holden and Jai based on a lot of earlier work, and it's again related to matching. So this is the picture you saw before, and the kind of partition you get here is really much nicer. So this is the fair partition into, again, so in this case it's happening on the sphere, not the torus, but you could do the same on the torus. And the basic method here is that every center applies a force of gravity, two-dimensional gravity, to the points of the sphere, and every point moves according to this gravity, using that as a gradient flow, and yields this partition. So, again, there's a lot of relevant history for this method, which I will discuss tomorrow in the colloquium. But this method does yield equal areas and turns out to be also more efficient than the other one in terms of the distance traveled from a typical point in the territory to the center. There are still many open problems to understand this method well. So I'll get to that tomorrow. Any questions about any of this? Okay, so the final example I wanted to tell you is it's a public lecture. So this is some an amusing story involving a 100-year-old problem on piling blocks. And most of the work here was done by Mike Patterson and Uri Zwick, but then part of it was completed in joint work where Michael Toro, Peter Winkler, and myself joined them. So, last topic that I want to tell you about, and very classical, the overhang problem. So, maybe I'll do the slideshow. Dangerous. Okay, so what is the problem? We have a table and some bricks, and the goal is to get the bricks to hang as far as possible from the edge of the table. So, simple optimization problem, we have n bricks, how far can they go? So, what's the classical solution? Suppose I have 2 bricks, or maybe suppose I have 1 brick, then I can of course slide it until it just reaches half its length is hanging over the table. If I slide it anymore, it will fall. So what about 2 bricks on the table? So the top one can still go to distance half, but the one before, it can only go to distance 1/4. If I move it anymore, then this pair will fall down. And you can just iterate and see that the optimal solution of this type, where you just do greedy local optimization, each time adding 1 more brick, is just half the harmonic series. So when I add n bricks, I can get to distance 1/2n. And if I'm forced to just put 1 brick at every layer, that's as far as it can get. And this goes back like 100 years. And this is an example you can find in many old physics books and riddle books. Okay, but is this really the best? So these are harmonic stacks. So it's certainly not optimal. So here is an example with 3 bricks. Already with 3 bricks, this configuration does better. Okay, so it will go to distance 1, while this one went to 11/12. So the classical solution is not optimal, and there's this otherwise nice book, Mad About Physics, that explains the classical solution and then suggests creating this kind of wall and claims that this will be stable. And they actually, more precisely, they suggest to put 2 of these to create a diamond. And indeed, the 4 diamond is balanced. So this kind of picture is balanced. There, question? However, it turns out that the 5 diamond is unbalanced. And rather than showing the equations, here's a movie. Really is unbalanced. So analyzing this involves really writing down the forces and doing some classical statics. And what Patterson and Zwick found is that you can get, so I'm going to skip the example, and they found that parabolic constructions of this nature will be stable. So basically you think of a parabola and fill it with cubes, and then they do the statics to show that this is stable. So how far does this go? In a parabola, the number of cubes you get up to distance d will be total d cubed, because you're filling the inside of the parabola. So if it's order d cubed, so this is the exact number, order d cubed to get overhang about d, what this means is that if I have in my hand n blocks, I will be able to get to cube root of n. This is the Patterson-Zwick result. And so you can get to order cube root of n with n blocks. Remember, this contrasts with the classical solution, which was only half log n. So really, you can do much better. And this is something that does slightly better. The oil lamp configuration because we want to get far this way. We don't care so much about this. So this we just use for balance. So, and this is it's an exact picture with overhang 10. And one thing which was left open by Patterson and Zwick is cube root of n the best you can do? Because they had such a great improvement from log n to cube root n, and then they tried many patterns, and they could just get different constants times cube root of n, and that's where the rest of the co-authors joined in the second paper to show that indeed cube root of n is the optimal. And I'm going to finish with this and just say that the solution turned out to be based on some random walk type problem or splitting game. So what is the splitting game? You have a unit of mass at the origin. So it's a different problem. It turns out that because of the statics equations for the forces, this problem is very closely related to this overhang problem. So what's this other problem? We're starting fresh. You have a unit of mass. And the goal is to send a constant fraction of the mass, say half the mass, to distance n. So at each step, what you can do is split the mass, point to a vertex, and split the mass there equally between the neighbors. So the splitting corresponds to what the forces are doing in the overhang problem. So, but you can think of this problem separately from the overhang problem. You have a unit of mass. Your goal is to get half of it distance n, and each move you choose a location and you split. So you see now, so here 1 is chosen and the mass is split, so half goes to 0, half goes to 2. Now -1 is chosen and the mass is split, and again we get this picture and so on. And so each time you can only choose one location and split the mass there between the neighbors. And the question is, how many such steps are needed to get to distance n? And turns out that's the same as asking, not clear reduction, but how many blocks are needed to get to distance n in the overhang problem. So if I am in a splitting problem, how much do I need to get to distance n? So here random walk can guide us. So if I look at random walk on an interval from -n to n, if I want the random walk to go with probability half outside the interval, I should run the random walk for time which is about n squared. Classical, easy factor one. Now, the splitting game is close to random walk, but not the same, because in the random walk, really at every time I'm splitting the distribution at all locations. Wherever the particle is, its distribution in the next step will split from the current distribution. So one step of the random walk kind of corresponds to n steps of the splitting process. And this really suggests that for the splitting process, you need n cubed moves to get half the mass to distance n. And however, the splitting game has much more freedom than the random walk, because we're allowing to do any pattern, any algorithm of choosing one site at a time and splitting the mass there. So we had to give a different proof that indeed n cubed moves are needed, and that eventually led to showing that cube root of n is the maximum distance you can get in the overhang problem. So these papers can all be found in the Math Monthly from 10 years ago, but is there a question? Okay. So let me end here and have to answer any questions.